evening and hello, everybody. It has been an extended season of joy and celebration for the structural engineering community. As you may recall, in 2021, Professor Sudhi Jain was conferred the Padma Shri by the President of India. This was in recognition of a life which has been dedicated to earthquake engineering and earthquake safety of the built environment. And now, close on its heels, Professor Dipti Ranjan Sahoo has received the prestigious SS Bhatnagar Award for his amazing work in energy dissipation devices, amongst other things. We'll talk about the two gentlemen at a little greater length later. But for me, these two awards have heralded a coming back of sorts of the structural engineering field. Most people had written off civil engineering. It was the least desired field of engineering, with hundreds of seats going vacant each year. And the recognitions have willy-nilly developed a renewed interest in the field of structural engineering. It has caused us to hold our heads high amongst our other engineering colleagues. What is remarkable to me is that young students, academics, and professionals seeking a career in structural and earthquake engineering now have multiple models in front of them. I'm not for a moment suggesting that these are the only achievers in the field. No, not at all. But Professor Jain and now young Professor Dipti Sahoo are some of the most recognized persons in recent times. And I've had the opportunity to know both of them, and I would consider it my privilege. Dipti Ranjan Sahoo is known to me since his student times at IIT Kanpur, and I've known Professor Jain since 2001 after the Bhuj earthquake. Professor Jain has also been a teacher of Professor Sahoo at IIT Kanpur. Dipti Ranjan Sahoo had joined IIT Kanpur just a few months after the Bhuj earthquake. Correct me if I'm wrong, Professor Sahoo. And I think that was perhaps the most exciting time to be at IIT Kanpur. You know, for the next 10 years, IIT Kanpur was the hub of earthquake engineering in India. Professor Jain, Professor Durgesh Rai, who was Dipti Ranjan Sahoo, Professor Dipti Ranjan Sahoo's PhD guide, and Professor C.V.R. Murthy, all three internationally known earthquake engineering experts, were together at IIT Kanpur at that time. That place was really a beehive of activity and excellent work in the field of seismic engineering. The objective of this session we're having today is to felicitate Professor Dipti Ranjan Sahoo and hear about his research and the development work that has led to this recognition. But just as important, I believe, is the understanding of how one may develop a scientific temperament to reach the level of good work, which has been demonstrated by him. And who better than our own Professor Sudhi Jain, who time and again has demonstrated what it is to have a scientific temperament to guide us in this. So let's have Professor Sudhi Jain share his thoughts first about the development of a scientific temperament. But before that, just indulge me for a few more minutes in giving a brief introduction to the two gentlemen. Actually, I think most of you know a lot about both of them, but I still think I should do the motions of formally introducing them. I have prepared just about 3 or 4 slides each, and I think I'm preaching to the converted, by trying to tell you about him. But I thought I'll just I'll try and cull out some interesting information about Professor Sudhi Jain. So Professor Jain had completed his Bachelor of Engineering at the very young age of 20. Okay, in 1979, he had completed his bachelor's. Now just look at this. Okay, in 1983, that is 4 years after that, he has completed master's, PhD, everything, and from the most prestigious California Institute of Technology, or Caltech as we know it as. Then Professor Sudhi Jain joins IIT Kanpur, and it is a measure of how rigorous and how difficult the process was at that time to become a full professor. And yet Professor Jain was a full professor at the age of 36. And he became the director of IIT Gandhinagar in 2009. He was the first ever IIT director to be given the 3rd term. But his services were required more at BHU. And so midway through his third term, he joined as the Vice Chancellor, where he is presently at the Banaras Hindu University. Um, let me just see. Yeah. So, I think most of us know about Professor Jain's achievements. He has been a champion for earthquake engineering education and earthquake engineering practice in India. I would say that in some ways he ended up being such a rock star in as far as the dissemination and sensitization of earthquake engineering in the country, that one of the complaints I nowadays have as practicing engineers, that young engineers who are coming out are more worried about the buildings in behavior during earthquakes, and they are not in the least bit bothered about worrying about the 24/7 gravity loads. So I would say that this in a way is a compliment as to his persuasive abilities in putting the agenda of earthquake engineering in the forefront. And I think that definitely everybody would accept that he has been the principal leader in this field of earthquake engineering in India. He's also been one of the leaders in the development of seismic codes of India. And I hope that there'll be more participation from him in the time to come. He's also created numerous institutions, one of which is NICE. I think anybody who is presently in SEFI must have at some point in their lives gone to the NICE website or gone to IIT Kanpur and tried to utilize the resources available at NICE. He's also created various capacity building programs for teachers, for architects, for practicing engineers. And there was a program called NPEEE, and then there were other programs for engineers and architects and so on. And he's, of course, also the co-founder of SEFI, as I think all of us know. I'm not going to talk about his major achievements. Everybody knows it. I think there are two pictures here. The picture at the top is the IIT Gandhinagar campus. And if any of you have had the good fortune to have gone and seen it, you would see it's an amazing campus. I think I would also very strongly encourage you to go through a manual or a book they have about how they've gone about creating the campus, right? From starting with how did they go about selecting the architects and the other stakeholders. I think it's a great learning process about how to build a campus of this size and the landscaping which it has. It's an amazing campus. I think one of the other during my time, as I know Professor Sudhir Jain from 2001, so it's been really a long association. I've just been very impressed with his, again, I'm using the word persuasive abilities, and that has helped him in good stead for mobilizing huge amount of resources for whichever institute he has been in, whether it was at IIT Kanpur and then later at IIT Gandhinagar. And I think, at some point when he retires from his numerous, I don't know when that is going to be, I think he needs to also, teach all of us how to be good in these other areas besides structural engineering. As I said, that there's also a second picture, which is with Professor Jain with the girl students of Banaras Hindu University. I think the picture speaks 1,000 words, so I'm not going to say any more. So he has been going about developing a very fresh ethos at the Banaras Hindu University as a vice chancellor. It shows his courage. It shows his ability to carry everybody together, his ability to bring in harmony. And also, as he has himself once said, his aim is to build a culture and atmosphere where the people are motivated and spirited. So I think, I'm looking forward to hearing Professor Sudhir Jain talk about how do we develop a scientific temperament. Just so that we do not have a break in the thread of the two talks, if you will, I may also introduce Professor Dipti Ranjan Sahoo. so that, after that, Professor Sudhir Jain can take over. But before that, I just wanted a last slide to share and about what I think about Professor Sudhir Jain. And it's not, I mean, the four bullets are not in sequence. It's just, I would actually say he's an ideator first. I mean, I think at any time his mind has like 10 big ideas, floating around. And I don't know how he manages to control all these various ideas, which are like, like atoms just striking at each other. I think it would be really interesting to know how he manages that. And he's an educationist. I mean, he's spread his range from being just an earthquake engineer to being an educationist. And I think at one time I remember he told me that maybe in some other time I would like to reinvent myself as an educational advisor, advisor in how to start universities, how to run universities. And I think he would be great in that. And he's been a fantastic capacity developer amongst his students, among the people who worked with him. So I think he wears a lot of hats, and we will look forward to hearing his talk. And let me now go to let me also introduce Professor Sahu. As I said, Dipti Ranjan Sahoo for us, and that is some indication of how old we've all grown, right? For us, Dipti Ranjan Sahoo was a young little student when we were talking, when the earthquakes had struck in 2001 in Butch. And he right from the very beginning, he has been very much interested, and he did both his master's thesis and his PhD thesis with Professor Durgeshwar. So he has very long relationship with him, and he has continued working in the area related primarily to earthquake engineering and primarily related to energy dissipation devices, which could be, so he did his thesis on these aluminum shear yielding dampers, and then he's moved on to various other dissipation devices. Of course, he has interest in a lot of other fields. And so, this is again, trivia. So he finished his PhD in 2008, and 12 years later, he was also professor at IIT Delhi. So I think that's a great achievement. And Professor Sahu's, major achievements, I guess all of you have had the chance to see it. I just picked up a little, I'm sorry if I have broken any copyright, but I just thought it was such an interesting illustration. So I just took the liberty of putting it up here. And he was already picked up as an INA, Indian National Academy of Engineering Associate, way back in 2012. And he's also won the Young Scientist Research Award and the DST Young Scientist Award. So he's really won a lot of the awards which were available for a young faculty member or for a young researcher. So I think that his skills, his abilities have been well recognized. Because he's been very prolific in his research, in his papers, and I think he is one of the very high Scopus Index also, which I saw. So I think all of us who were in the INA and being part of the selection, and then we would see the Scopus Index, and we'd always have to argue that structural engineering, you can't have a high Scopus Index because it's not. And then I looked at yours and I said, now there's no argument, he really has one, so he's beaten everybody to it. So I think that Professor Sahu has displayed amazing ability at a very young age, and I think Professor Sudhir Jain and of course Professor Durgeshwar must feel very proud of their student, their protege, if I may. And I would like to hear what they did right, and what was the special bright spark that they had seen in Professor Dipti Sahu. And as I said, the principal contributions of Professor Sahu have been in energy dissipation devices. I had actually once connected with him for buckling restraint braced frames because it was something which I was very interested in. And I remember I even talked to him about steel plate shear walls. And so, he's always very interested in trying out new things. And he's a fountain of energy and excitement. So I think it's a joy to work with him, especially when, it's not about just getting a project peer reviewed and stamped, because that's what unfortunately now a lot of the IITs have to do because of the pressures from various authorities. I think Professor Sahoo was very different, refreshingly different, if I may say that. So here, I would like to stop talking because really we've kind of congregated to hear the two speakers, the two celebrated and recognized leaders in this field. So over to you, Professor Jain. Thank you.
All right. Thank you, Alpa. I don't have slides in my current role. I don't get time to do justice with these kind of expectations. Thank you for your very generous introduction and for this opportunity to come back to the structural engineering community. I see almost 100 plus 110, 115 people showing up as the participants. So this is a life that I left behind. And once in a while, when I meet people in structural engineering background, I'm really delighted. I'm very, very proud to be claiming that I am Dipti's I have been Dipti's teacher, as I have fondly said that we teachers get reflected glory of our students. If our students do well, we become well known. We claim that we are their teachers. So I'm really, really proud of Dipti and for what he has done and what he continues to do in his career. And I wish him many, many more successes. Now, the topic that you gave me to talk about is how to develop the temperament for research in structural engineering community. Let me start out by first asking a question. What is research? Is research publishing papers? I had a very pleasant experience some 5 years back. We were looking at a faculty candidate in IIT Gandhinagar, and one of the assistant professors came to me and he said, Professor Jain, we have a very good candidate, but he seems to think that publishing papers is research. Aha. And it was a great satisfaction to me that an entry-level assistant professor that I had earlier recruited was able to understand that publishing papers is not research. To me, research is really about solving problems, about pushing the boundaries of knowledge, about knowing something substantial which was not known up there. And if you look at it from engineering perspective, as engineers, for us, research means solving problems. And one can say that every structural engineering project is different, every building is different, so you're really solving problems all the time. And I think that would be absolutely correct. So when a structural engineer looks at a project, they have a new challenges, they have new challenge of the foundations, they have new challenge of the loading, the new challenges thrown up by very fancy architectural configuration. They're really solving problems. So structural engineers are already into research if they do good research, if they do good structural engineering, because for every every good structural engineering that we do, we also do a lot of bad structural engineering. And we have serious concerns. We will come to that later. Now, going back to research, if it is not publishing papers, then what exactly is the objective of research? Why are we doing research? So to my mind, there are two reasons somebody is or should be doing research. One is to earn credentials, and second is to make an impact. And these two need not be aligned. For example, I got a PhD, so this PhD required me to do research, and now I have a PhD. Now that is establishing my credentials. Whether that research was useful or not is not important. I published 20 papers, I published 30 papers, I published 100 papers, and I boast about it. To me, that is credentials. Whether those 20 papers anybody read, whether those 20 papers change the way the structural engineering is done, is not important. My credentials are good, people recognize me that I am good. The second is impact. Impact, as I said, it is either to push the frontiers of knowledge, to push the boundaries of knowledge, or to do problem solving. And for structural engineering context, it is problem solving. So the question is, what type of problems do we want to solve? Typically, the problems that we want to solve will come sometimes unannounced, sometimes they will come announced. And those of you who have heard me speak earlier, some years back, my discovery of the reconstruction project in Balochistan, the way they came up with the earthquake-resistant construction in Balochistan in 1930s, to me is a very fine example of solving problems. Or the discovery that I made in Port Blair, where in early 40s, they had done seismic retrofitting on masonry, churches and mosques and things like that. Is a good example of problem solving. So when a structural engineer does good structural engineering, maybe to try to optimize the material, to optimize the cost, to use newer construction technology for his project, they're also doing some research in some sense. Now, when we talk about good structural engineering, which is problem solving oriented, what is the role of education and training? What is it that, how is the foundation laid? To my mind, there is a fundamental problem in engineering education, not just in India, but the worldwide. And that problem is the following. The problem is that our entire focus of engineering education is how things are done. So somebody would come and teach how concrete building is designed, how concrete beam is designed, how concrete column is designed, how concrete shear wall is designed, how earthquake force is calculated, how reinforcement is detailed. We don't talk about what is to be done, why it is to be done, for whom it is to be done. These are perhaps to be told by somebody else. Now, let me illustrate this point differently. When I used to meet the first year students at IIT Gandhinagar, very bright young kids who had done JEE exam, very competitive exam, and they were really bright, I used to ask them, do you know what is mean and do you know what is median? And everybody knew it, everybody, no exception. I would write 5 or 6 digits on the board and I would say, all right, you young man or you young woman, can you tell me what is the mean or what is the median? They would always tell me. Then I would ask them, all right, tell me when I will use mean and when I will use median. I never got a right answer. Never. Never. I tried this on faculty candidates in mathematics who claimed to have learned courses in statistics. And more often than not, I was disappointed. Now, here is the situation. I explained to my first year students at IIT Gandhinagar that a typical IIT education, a typical JEE preparation is teaching you how to calculate mean and how to calculate median. But you're not learning when to use mean and when to use median. When you go to a company, will the company make you the boss or will make the other person boss who knows when to use mean or when to use median? Because if you know when to use mean and when to use median, you can easily hire somebody who knows how to calculate mean and how to calculate median. But if you make the boss who knows how to calculate mean and how to calculate median, but he does not know when to use one, cannot be the boss. In other words, the boss will be the person not who knows how to calculate mean and median, but the boss will be the person who knows when to use mean and when to use median. Same thing holds for structural engineering. If I know how to design a bridge, but I don't know why this bridge is to be built, what is its implications, for whom I'm building it, what are the implications of traffic and all that stuff. I will be a technician designing the bridge. Somebody else will be the boss of the highway department who will decide where to build the bridge and whether or not to build the bridge. In other words, we must include now why something is important. That is humanities. For whom this project is to be done. That is social science, society, sociology. What is to be done will be perhaps policy, it can be social science, it can be even architecture. And then how it is to be done, that is engineering. So the engineering education, to me, if we start to rethink and say that, all right, we will talk about why it is important, for whom we are doing it, what is to be done, and how it is to be done, then there is a complete engineering education. And you are now producing a holistic person who would be able to do a project. Now let's go and zoom in further. And we talk about how it is to be done. Now, when you talk about how it is to be done, and you are again talking about a bridge engineer, that bridge engineer should know a little bit about traffic, a little bit about economics, a little bit about geotech, a little bit about hydraulics, because there is a river there, something about materials, something about construction technology, because if you don't know how the girder is to be launched, how would you handle it? And of course, it would be wonderful if you know something about aesthetics in addition to the structure. Now, how do we do that? If you look at any of the good institutions, MTech curriculum of structural engineering, you will see advanced structural analysis, theory of plates and shells, theory of elasticity. You may have a course on advanced design of concrete structures. You may have a design of pre-stressed concrete structures and things like that. The moment you try to put to a structural engineering MTech program, a course on geotechnical engineering or hydraulics engineering, both structural engineering teachers and the students will protest. They think, structural engineering padhne aaya hu main. Why are you forcing me to learn geotechnical engineering or hydraulics? If you try to teach them to go, tell them to learn a course on humanities and social science and learn some economics, they will say, why we are learning economics? So I think we need to look at our engineering education with a totally fresh mind. And how do we do that? To me, there were three key ideas that I would like to propose. One is we need to teach engineering from the mindset of whole to parts. When I was learning my surveying class in my second year of civil engineering, this was a phrase that my civil engineering surveying professor used to use, that you go from whole to parts. You first look at the whole property, the whole land on which you have to survey. You get a sense of it, you do some reconnaissance, then you do some triangulation, establish a few points, and then you go into details of it. You don't start from one side and hope that you will go to the other side step by step. It doesn't work. First, you have to go whole and then go to the parts. Similarly, when we are talking about the design of a building, design of a bridge, we go from parts to wholes. We start with a beam, we start with a column. We have to start from a building, and we have to say, okay, we have to design a building. Guys, let us see how we are going to design this building. And this building happens to have a beam. Okay, how do we design the beam? And things like that. The second thing that I would like to say is that we have to do learning by doing. We have to do things. We have to let our students go to the site. We have to learn, let them have a visit on a place where there is a bars being bent. We have to make them do some drawings. And third key idea, I think, is that our structural engineering education has to have a very strong component of working with the practitioners, learning from the practitioners. The entire engineering has been totally distorted because the entire educational landscape of engineering has become very, very non-practitioners teaching. People do a PhD, they write a few papers, they start to teach, and they have never designed a building, and they start to teach. So I would not like to take too much of time here. I'd like to close and let us all hear Dipti Sahoo, in whose honor we are actually meeting today. So I don't want to take more time. I want to only say we need to start thinking of both structuring and research together, not in isolation. We need to see how we can do structuring projects better. And to me, that itself is a problem-solving mindset. That still itself is a research mindset. You have a project, you have a problem, you don't know the solution, you have to go and learn, you have to go and study, and you have to perhaps innovate. Second, when you say research for credentials versus research for impact for whom? Obviously, the community, the society that is paying for it. In other words, am I publishing a paper that will be helpful to the ecosystem in which I am working? Will it be relevant to the engineering community, to the society in which I am living? Or is it something that is going to help a society which I'm not living in? For example, I could be publishing papers in American Society of Civil Engineers, which will be very relevant to American construction typology. But those typologies don't exist in India. And Americans would gladly publish those papers because those are relevant to American typologies and it will help American society, but doesn't help Indian society. It helps build my credentials, but it doesn't make impact to my society. On the other side, I may be working on India-specific projects, India-specific problems. And I say, aha, here is this is a problem to be solved so that we can do better. And obviously, American Society of Civil Engineers will never publish. That's okay. You will end up publishing it from some journal in Delhi or Mumbai, and you may not get that much credentials, but that you will have that impact. So, to my mind, the issue of impact has to be seen with the glasses or with the prism of India specific. And of course, to do good research, one has to do basic training in research, the experimental methods, data analysis, writing, because a lot of good people, they are able to do good research, but they never learn writing. They are never able to put their ideas properly. They are not able to put the data properly, and they lag behind. They are not able to convey their ideas. So these are some thoughts that came to my mind that I thought I will share with all of you today. Thank you, Alpa, for this great opportunity, and my very, very best wishes to Dipti Sahoo for his continued success.
Thanks so much, Professor Sudhir Jain. And we are going to take 2 minutes just to kind of I guess, virtually felicitate Professor Dipti Sahoo. I think SEFI will independently also be in touch with him for a more direct felicitation. But I think, Sanjeev, you would like to kind of just flash something or and I guess after that, so we're really proud. We're really proud that Professor Dipti Sahoo is been a part of SEFI for a long time, and he has been a trailblazer in getting this award and showing the path for future young researchers and academics. So congratulations, Professor Dipti Sahoo, Dipti Ranjan Sahoo, on winning this Shanti Swarup Bhatnagar Prize. We're so proud of you. And now, if I may, shall we call Professor Dipti Ranjan Sahoo to give his talk, because I think we're also very interested in the work you've been doing, which has been recognized. Thank you.
Thank you. Thank you, Ms. Alpa Sheth. First of all, my sincere, I'm very, very grateful to SEFI for providing a platform to interact with the structural engineering community. And this webinar is actually kind of, for me, it's special and important. Because why it is special? Because I am going to speak what I've been doing in front of my teacher. Professor Jain has been my inspiration. Yes, you are right. I joined IIT Kanpur, 4 or 5 months just after Bhuj earthquake. So 26 January was the Bhuj earthquake, and in July I joined IIT Kanpur in masters. And I think there could not be any better time to get exposed to what is earthquake engineering. And so that gives me a lot of interest to work. And yes, IIT Kanpur at that time was, probably only one and topmost in the world, I can say, in terms of earthquake engineering. I was fortunate enough to get my teacher, my supervisor, Professor Durgesh Rai, who actually, helped me to explore new idea and work something interesting and which can be implemented at the site to the society. So most of my work which I have been doing, looking at the practical problems, and that in that sense, so most of my work is the experimental, and which is I learned from my supervisor again. So that's why this becomes the special case today, because I'm going to speak about my work. The second one is important because within last 24 hours we have been a major earthquake, kind of magnitude 6.4 in Nepal, and where we lost more than 150 people, and there are many injured actually. So in that context, this webinar is also very, very important. So what I'm going to do, I quickly highlight what are the work my group, as my students, and we are working. And so I will be totally highlighting on the work which is relevant to energy dissipation. So the topic is structural fuses and buckling resistant braces. I will also talk about the applications in new construction and the retrofitting applications. Before I go to the topic, so I like to acknowledge my students. So essentially, I am taking the credit on their behalf. They are the one who are actually doing the experiment analysis on. So I'm just supervising them. So they are the real champion for this. And so my PhD students, past students, and the current students who are working right now, my staff members, department, IIT Delhi as a whole, the collaborators all over the world, and the funding agencies, and most importantly, the family and parents support and the motivation I have been getting till date. So just to outline today's presentation, I will just briefly talk about the introduction. I will actually try to highlight two things. One is called the damage control design. One is called the resilient design. Then I will come to the practical application and what are the challenges. I thought that will be most useful for our young engineers, researchers to think differently in the context of seismic design. So till now, what we have been doing in the earthquake resistant design is like we don't design a structure to remain elastic because it has the inherent properties of post-fixed strength, where it's the material or the redundancy. So we actually expect that the structure should go to the inelastic range, and so in a sense, instead of like going to a linear elastic behavior, we are going to or we expect that this would be elastic behavior, and then that means you are actually expecting on some kind of damage in the structure. So you will get under cyclic loading, you will get some energy dissipation in terms of the damage in the beams and columns. One important point to note is like here, so we are relying on the ductility of the structure. That's why the conventional design procedure we called as ductility-based design. Now, if you look at the basic design, this is essentially the mass into acceleration, and then that force we get, and we actually design the structure to behave non-linear way. But if you look at more clearly, so there is an equation which is called the energy balance equation. So the kind of input energy you are actually sending to your structure, that somewhere it is actually getting balanced by so many factors. One of them is strain energy, which you get from any member. One of them is kinetic energy. Then every material has some damping, and then the most important part is the hysteretic part, or the so-called the damage part. So what are the strategies, like if you need to reduce the damage or reduce the collapse of the structure? So essentially, in the same equation, you probably have very limited chance for a given structure to change the static or the strain energy component to change the kinetic energy component. What I can do is I can actually increase the hysteretic energy component, or I can increase the damping component, or I can increase both of them. So the first part, it can be done by adding some additional members, which called as the stiffening. It can be simple brace also. The second component, which can be done by adding an actual damper, which, there are so many concepts on the damper. So the more easiest concept we actually thought of, like some kind of viscous-based dampers. But if my stiffening system is not again going to be, let's say the brace is not going to be elastic, that at some point in time, it is also going to be the hysteretic energy, and we have some damping from the hysteresis as well. So in a sense, these two components, if we can actually control or enhance, so the energy balance equation or the input energy can be actually controlled well without damaging our beams and columns or primary structures or primary components of any structures. So people can ask, when you are stiffening the system, then you are actually attracting the higher seismic forces. The question here is, I am not expecting that it will be elastic. It will be actually kind of sacrificial element. So when you have additional damping, that means your response spectrum, if you see that your peak values will keep coming down. So based on this, so all the devices which I'm going to talk about, so one component is the structural damping, and every member has, or a material has some kind of damping. I'm not talking about the inherent damping actually. I'm talking something about the added damping, like damper or the friction-based damper, any damper, so that you can increase the added damping component. And just to give a comparison of the inherent damping, any material, like that like 1 or 2% for the steel has a damping, 5% of concrete has damping, that we call as the inherent damping. So if we add a device which can give you a higher damping, so you are reducing down the response of the structure, you are reducing down the impact or the design force to be considered for design of a new structure or any retrofitted structure. So based on this, so out of all the damping characteristics, we know it can be based on the friction, it can be based on the viscous. The most important thing, which probably I feel is the most of the least expensive way to get this, is the hysteretic damping. And it is essentially through the metallic yielding. It can be steel, it can be aluminum, or it can be any other metal. And so you rely on expanding this area, so that the more the area, the more energy is there. So that's why called, if you can actually take, compare with the hysteretic damping, you can get some approximate idea that what percent of damping we can get for a given material or given configurations. So with this as the background, so I'm going to talk about two things. One is called the damage control design, which we say that, okay, you have a strong column, weak beam actually kind of concept. So which is essentially the ductility based. So instead of your, in linear elastic system, you have a non-linear elastic system, but essentially you are trying to see that the most of the energy will be dissipated through the hysteretic damping. In this kind of structure, in this kind of design, the goal is to get a life safety level of protection. So in some cases it is good. In some cases you probably need to go beyond that. So that I'll come to the second part of this presentation. So do this, one thing I have already explained, that either we can use a stiffening system or we can use some kind of additional damping devices. And very commonly we call as the anti-seismic device or the structural fuses. So at the same time, you have to also make sure that the overall cost of this, stiffening system or the, developing a device should not actually be very, very expensive, so that it can be used by, so the overall cost of the structure should not actually increase significantly. What, based on the available materials, one of the materials is steel is probably like widely used, particularly in the context of India, where the one of the topmost producer of the steel. If we can exploit the steel properties in different ways, it can be used for both concept, either as a stiffening concept or as a device concept. The advantage is it's not a mechanical device, so maintenance cost is also very, very low, and it can be actually customized to get the kind of or the desired level of protection to the structure. So let's say I have a steel plate. I can actually pull it in the tension and compression, which we do in the first year or second year civil engineering courses, to find out the stress strain curve actually. Now, if we actually do the cyclic loading, so what happens that in one part you will get strain hardening, yielding, other part you have the buckling. So we have been using this concept as in the concentric brace frames. Now the question is, the whole idea of the seismic design concept, which is based on ductility, is to get a wider hysteretic loop. So if we can have some mechanism, we know that like any steel member has a buckling. If we can actually control the buckling of the structure or the element, so you can get a kind of stable hysteretic loop with a bigger area, with a bigger energy dissipation. The second one is same steel plate. If I actually orient in such a way that the loading is in plane, so we can get the shear loading, that is called, and that gives you also the hysteretic loop is par with your tension loading, either in tension or compression. The third part is same steel plate. If I can orient in such a way that it takes care of the out of plane loading. So, for example, these are some series of plates. So if you do the cyclic testing, you will get some kind of flexural yielding, and that gives you the hysteretic response. So the same plate, if I can orient in a tension loading or the shear loading or flexural loading, I can exploit and I can get some energy. So taking that, so what is the strategies to get the hysteretic damping? Of course, the energy dissipation is there. So I'm going to talk about these two things, which is mostly based on the steel. So one is in the stiffening system, one is on the structural damping or the added damping system. So one of the common thing which we use most of the cases, whether it's steel or concrete building, is use the brace. So now you see the typical brace, typically we use in a kind of a pair of brace. One brace goes in tension, one brace goes in compression. So in the compression, you will see that once it's buckled, you lost a lot of area. You don't have that kind of energy. But it's not that simple. It is not only the brace, the connection is also play an important role in any kind of steel brace frame. If you see a typical experimental behavior or actual behavior of the brace buckle something like this. That means there will be some kind of damage here, that will be some kind of damage at the middle and the ends. Now, at the end of the earthquake, actually, either you have to remove the complete brace or you have to remove your brace with the assembly. So there are two concepts. In American concept, they use the weaker gusset plate. In Japanese concept, they use the stronger gusset plate. In India, they use both actually. So the idea is, can we have a better connection system, which probably behave or give you more energy? I'm talking about both the ends. Or the recent one, what we have said is, since anyway you need to have some energy dissipation at the ends, can we actually use some kind of fuse system along with your brace? It's a simple system which can be added to both ends or only one end of the brace. And you can see that this is one of the test results I'm showing. You can reach up to 5% drift. In the typical brace frame, getting 2 to 2.5% drift is very, very tough. Now, as I said in the previous example, actually, so you have a buckling problem here, and can we reduce down this problem, or can we have a loop where this area is covered? So taking that as the clue, structural analysis, we know that there is a concept called the buckling. So if you actually provide the more restraint, your buckling strength is increased, and that gives the basics of the buckling restraint brace. is the same brace system or same structural tube or the plate. What you do is you actually put it in a sleeve, and without there is no composite action. And the idea of that sleeve is it just provide a kind of a preferential direction movement, actual movement of the plate. So that is something I'm trying to show it here. You have a plate here, and which is actually placed inside a tube. Of course, there are some, different materials can be used. The only thing I'm talking about here is not a composite member. It just stays there just to prevent the outer plane buckling of this plate. So there are so many components involved in this buckling resistant braces. So what we have been actually working on, or we have worked on, like to optimize this. That is number one. Number two is these braces are quite expensive. So that's why, like in India, can we make least expensive braces using the local material which is available in India? And the third point is looking at the society. Can these braces, unlike other construction, can be made at the site? So looking at all these things, which we developed this brace, which is called a all steel buckling resistant brace, which is it gives you the inspection after the earthquake, how it behaves. It gives the on-site fabrication, and it actually can be implemented at the site with the least cost. The cost part, I'll come to the later stage during the discussion time as well. So this is one of the typical BRV which we have developed, and you can see that how they are performed in the testing. So we have done some testings here, and some of the patents are also mentioned here. Now, if you see typical structure, that's how the BRVs can be placed. So instead of simply putting a brace, which is, as prone to the buckling, a BRV is a good option, provided the cost is par with your concentric brace springs. The second system I'm talking about, the structural steel plate system. So whether it's steel brace or the BRV, they work in the principle of axial yielding. That is the first concept I said. The second concept is the plate, use the plate and ensure that the plate is yielding under shear. So this is let's say a structure where only a small, you can see these two parts are subsummed. It's similar to the shear wall, which you use the concrete shear wall, but instead of concrete shear wall, it can be very thin steel plates. And this is one of the, I can try to show the video here. Okay. So what happens that, like when you apply the in-plane shear, so essentially this is a very thin steel thin plate, and it actually behaves or like, it will buckle. But once it is buckled in both direction, you will see that it will try to act as a, some area of the steel plate, you can see that it acts as a, plate in tension. And that gives you the hysteretic behavior, which probably we are looking at, like there is no instability and there is sufficient strength and the stability involved there. So this is one of the tests. You can see, like when it's going to negative direction, you can get, some diagonal strip which is active in resisting the loading. The third system is called the steel truss moment frame, which sometimes is called as the column free structure. Column free structure means in the concept of not using the typical beam system. So it's an open girdle system. Like instead of beam, you use a small truss in the same structure. And when it actually you apply the lateral loading actually, so this part is called the variable part. It's, it actually deforms something like this. You will get the plastic hinges here. So the shear and flexural yielding will help you to give this kind of energy. This is the experimental curve. Again, we tested for 30 feet long steel plates, steel truss moment frame. This is a new concept. So only thing is, like, instead of using a kind of rectangular beam or a steel beam, it's just a truss which is replacing your beam. The advantage is in the buildings, both the panels can be used for the units, and the middle one can be used for the corridors. And in this panel, you can actually allow the ducts to, whether it's a electrical duct or any kind of service line can be placed there. Coming to the structural fuses, actually, so all the system I talk about is the stiffening system. Structural fuses is just a small device which will be installed in the a structure, and the whole idea is that whenever there is an earthquake, the first one to be damaged, taking or absorbing the energy is that system. And if you correlate to the electrical engineering, in every unit, there is electrical fuse. The whole idea is whenever it is there, whenever there is a high voltage, that fuse burnt away. So that is the same concept is here. Again, the concept I'm using here is using the steel, how to make the small, units. It comes from your buckling resistant brace, where it can be made as small as possible. But the concept here is little different from the whole BRB base. But nevertheless, I'm not going in detail to that. But it's a small device which can be actually held up by lifted by only 2 persons. It can be installed at the site along with the brace or at any location of the buildings or the bridges. The second one, again, it's a small shear link, which actually I extended from my PhD, which I did at IIT Kanpur. So it's a shear link with a multi-panel, and it also takes care of the shear yielding and flexural yielding. The triangular plates act as for the flexure, and these plates actually act as shear plates. The problem is like this needs to be replaced. You can see the tearing of the plates in high seismic loading. So what we actually extend is like if we can prevent the buckling of this plate by some kind of mechanism, essentially to develop some kind of sandwich system, whether it is a steel core or the aluminum core, you can see that like the complete buckling is prevented, and you get a very stable hysteretic loop. Now, coming to the second part of this series, so till now, this is where we are looking at, like in terms of seismic design, that in case of earthquake, the goal is to save the people, so it's the life safety. Now, in this process, what you do is, so if you remember the previous slide, the intention is to widen or get a bigger area. But at the end of the earthquake, what happens that at the end of the earthquake, what happens? So you will be here. So that means there will be residual drift of the structure actually. So, and when your structure is at tilted position, so probably like, sometimes it is, even if it's okay in the stability point of view, it makes, impression that like, it's not safe and it's not habitable. So if you are looking for the fully operational level, so your structure at the end of the earthquake need to be pulled back. So that is called the recentering and self-centering thing. So this, shaded portion is a system where, or the hysteretic loop for a self-centering system. So here also I'm going to talk about two systems. One is the device, what kind of devices we can develop or we have developed, so that it has, rather than a fully, hysteretic response or loops, at the end of the day, it should come back to nearly original position. And the second one is we can combine to a system where your self-centering device is there and a system is there. They're working together to pull back the structure to its original position. So this is the first system. Before I'm going to detail of this device, if you see the hysteretic loop here, actually, rather than you have a kind of a parallelogram kind of thing, there is a multi-stage, hysteretic response or loop. And you can see that if you just unload your system, it's actually pulling back to its original position. So it's a simple, concept, but doing that in practice. So we have used different kind of materials here. We started with the steel again. So it can be like, small BRB with a larger BRB system, which, one case like during the small earthquake loading, only one BRB will be yielded, whereas the remaining will be unyielded. And then when you do the unloading or higher loading, they both will combine, and it will give you this kind of hysteretic response. So this is one of the specimen I'm showing, which we have fabricated here and tested in our lab. That is called the FE-based super elastic brace. Actually, see, so we started with the steel, and we found that like the steel, which probably will be okay, but getting the recentering is difficult. So we collaborated with one of the company in India to give a product which has similar to the steel, but some characteristic with the shape memory alloy. So I will come to that, what is the shape memory alloy material is. So this is a typical application where the same system can be used. So coming to the shape memory alloy is a kind of a, a special alloy which is sensitive to the temperature, and it gives you the pre-stressing force or the resistance through a thermally activated phase transformation. This is one of the picture, video I'm showing here. So if you pull it, actually it will be there, and then give some sense, self elasticity or super elasticity, and then the remaining portion, once you actually apply some kind of heat, it will come back to original position. So we utilize this concept and talk to that company to make a material which is a combination of the shape memory alloy and the steel, so that the steel will give the ductility and this shape memory alloy will give you the recentering. Actually, this is typically like, typical behavior of a shape memory alloy. So if you see that, like, we try to use this with the BRB. So what we did here is, again, I have to show this video, so just excuse me. So if you see this, since it's a rod or wire, shape memory wire, so essentially these wires are actually covering all around the BRB, but the wire can't take the compressive force. You need a system where whether the brace is under compression or under tension, the wire has to be always in tension. So it's a multi-tube system. So inner one is the BRB, then there is another tube, then there are 4 wires or stands, and these stands are actually made from the shape memory alloy. So if you add the BRB behavior, which we essentially intended for the ductility-based design, and combine the shape memory alloy behavior individually, which you will get is something like this. In the typical ductility-based design, probably your residual drift at the end of the earthquake would have been here, but you can see that you are close to your starting position. That's one of the device. So it's more detailed about this. This is the BRB, and then this is the shape memory alloy, and then this combined to give a self-centering BRB. This is one of the specimen we have tested, or fabricated and tested at IIT Delhi. Now, coming to the self-centering rocking system, this is something where the it's based on the ancient structures. If you look at the most of the Greek structures, they are mostly freestanding columns. So there is no actually physical connections here. So they are simply allowed to rock and slide based on that. So, but these structures are actually like, they have survived so many earthquakes. So the idea of the rocking and sliding, so sliding essentially between friction at this, for example, at between 2 surfaces, can be actually also used in our typical civil engineering structures. That is how the rocking system actually integrated. Now, what to do? Like, let's say you have a building actually. So the building can be simply placed on few pillars actually, and these pillars have no foundations, there is no connections. Now, but since you have the significant weight of the building, so this can't be only steel or concrete. The best way is probably like to use a concrete filled composite structures, and so this can be steel filled tube. And if you need to have a recentering behavior, you can actually add the BRB, everything we are doing below the foundation, or you can have a steel pressing wires. It can be shape memory alloy based or any super elastic wires. I'm just trying to give you some kind of idea like where it can be used, these devices. This can be used at the base level. I remember that this is rocking system, so there is no connection of the column to the base. It's a simple free actually. So when you apply the lateral loading, this column will simply go up. However, you have some device which may be viscous based or metallic based or the friction based. It will just allow some displacement and then pull back the system. The shear yielding devices can be used between 2 powers and maybe steel or concrete towers. In the typical high-rise buildings, you have a beam which is called the coupling beam, and that is probably like one of the location we have tested that with few energy dissipation devices, it can actually improve the structural behavior or seismic behavior of this. The similar, so there are many applications it can be used, let's say at the beam column corners or simply at the panels. One of the interesting thing I'm saying here is like even the BRB can be used as your columns. So you design instead of actually like your typical conventional steel or concrete columns, the columns of the lateral load resisting system can be made of some kind of BRBs you design for that. It can be a series of BRBs, and that you will provide or kind of friction-based devices that can provide the energy dissipation and the recentering. These are the few other probabilities where this can be the devices can be used. In case of bridges, actually the same application can be used. One of the shear links or the yielding devices can be used between the pier and the superstructures, or in bridges we use the pre-stressed wires in the superstructures, but the rocking system can be used in the piers with pre-stressing applications, and there are so many ways this can be used based on the site conditions. There are some applications I'm showing the BRBs in the real life applications. Is a university building. This is a retrofitted structure, completely concrete structure, which is retrofitted by the BRBs. And you can see the only two bays are actually used here. That is considered for the retrofitting. This is again a concrete structure, but there is a collector beam was required, and then you need the BRBs to install that. That is after the earthquake, how to retrofit this structure. This is one of the tests we did at IIT Delhi. So one of the major problem in India is open ground story problems. And I think open ground story, if you see that this is a 2-story structure we tested, and the whole idea was, since the story is used for the parking, only few panels or few bays can be used to install the braces, because anyway the structure behavior is controlled only at the open story. So we use numerically you have tested several configuration related to that, and in experimentally we did this representative structure. You will see this here. So the top one is completely filled with masonry bricks, and the bottom one was actually which is essentially meant to be free for different applications. We use some kind of devices here, and it actually performed well in real hybrid seismic testing. For the retrofitting applications, I'm again showing this for the school buildings. We have been talking to some schools here, where you have the beams and the columns are there. They are quite old, and you can't actually demolish and do this. So this kind of applications or these kind of devices can be used there. High-rise building, there is no need to provide all these devices, all the floors. One of the potential location is the outriggers, where even a small BRBs can be adapted. Even similarly for the bridges also, there are 2 girders. In between 2 girders, the BRB can be placed. So just to conclude, what are the future directions? So of course, there are a lot of work need to be done in the structural control. We need to have the efficient materials. For example, like combining shape memory alloy is mostly used for the aerospace structure. Steel is used in the civil structure. So yeah, they have their own properties. If you combine those, and it actually give you additional benefits, additional advantages. And in addition to that, there are there can be any other material can be used in terms of the fiber, the carbon fiber, or there are so many large areas right now. The material research field is quite extensive. So there we need to have collaboration to make. The whole idea is the devices should be least expensive, it should be affordable, it should be easily implementable, rather than actually importing from the outside to the construction industry in India. The second one is the risk reduction, like how the strategies to be taken to minimize the risk, whether it is in a slum area or whether it is a fully engineered building area. So there are a lot of research has been done, but how to implement that in the practice, that needs to be done in the future. The third one is the early warning. People are working in the developing that, can we predict the earthquake? But one interesting thing here is, if you look at the earthquake, accelerogram. So you have a P wave, you have a S wave. Those are relatively on the lesser, damaging before you have a surface wave hit. So from the time you have a P wave and from the time you have a most damaging surface waves, there is a time. And if this time can be utilized to not, essentially preventing the earthquake, but making our infrastructure safer. So that has been done to some extent. The current state of the art is like do a real-time probabilistic seismic hazard analysis. But if we can extend this to the next one, for example, like in the real time, let's say there are 10 or 15 seconds gap you have, and then you integrate your this signaling system and with your sensors, then you do the integrating system, so that like during the earthquake it can be directly spread or can be propagated to the society, whether it's a bridge or the metro or this kind of structures. So that I call as the next generation early warning systems. With this, I need to thank again Ms. Alphaset for giving me this opportunity, and SEFI giving me this platform to share what we have been doing here actually. Thank you. Thank you so much, sir.
Thank you so much. I think it was a very, very interesting talk. I really appreciate. I learned a lot from it, and actually, I'm going to go through this again because to absorb what you've said, I think it's going to require a rerun, and we will be keeping this talk on the SEFI website. Am I right, Sanjeev? Yeah, and so it can be accessed by a lot of people who were not able to join in, or would want to, like me, hear it again. I think we're now going to open the house for some questions. We'll take about maybe 4 questions. I have one question, but I'm going to ask right in the end. Over to anybody who would like to ask a question. Kindly raise your hand because I don't see too many questions in the question and answer. So we'll ask anybody who would like to raise. Okay. Okay, so there's one question here, Professor Dipti Ranjan Sahoo, that how different is the system you showed from the eccentric bracing system, which also used a link beam as a fuse?
Yes, I think they are talking about the conventional or concentric brace system. So the eccentric brace system they have very good energy dissipating capacity, but the issue here is actually the practicability. So the most of the studies has been done. So once it is get damaged, what is next? How to get it actually replaced? Because it's either at the corner of the beam, which is probably like with the connection with the column, and then if there is a part of the passage also, this is not usable. And the second one is the test results have shown that the eccentrically braced beam frames, your essentially the girder becomes your link element. The beam becomes your link element, and the full scale test done at Austin and I think the Michigan, they have clearly it was noted that there are the wave buckling is one of the main reason why for the large earthquake, and it becomes a serious issue. It can be reused. So if you want to, it's good system, but if you want to reuse the system, it's a little difficult. So that's why like there has to be a system. So if that is the location where you have to go use some kind of devices, so why not the structural fuses rather than like, changing the entire beam, because the one part of the beam is completely, buckled under shear, or the, flange buckling or the way buckling is there. So essentially, like, again, to facilitate the easy replacement and to use the build or to make the structure reusable for the future earthquake.
Great, thank you. There's one question from engineer Dinesh Raj Patrai, and he's asking, how would you determine the potential location for providing a BRB in buildings for retrofitting? Are there any lines available on this?
So essentially, the technical guidelines are not available. Again, I'm saying that each building is actually different. So the most important point is your retrofitting scheme should not actually work in a negative way. Actually, like for example, if you put the BRB brace or shear wall at a location, which in turn give you higher rotation, kind of rotational mode becomes active. So it acts in the negative way of your strengthening or upgradation. So the scheme is very straightforward. We have worked with some practical problems. The first thing is you need to find out what is the current state of the building itself. You have to analyze that, and then you have that will give you the potential location where these BRBs will be effective. It's one can't say that okay, of course the ground floors will be more effective in the conventional way, but in ground floor there can be n number of bays. Which bay where to use, that all depends on what is the usability of your building. If your water tank is actually at the center or is at the one of the corner, or you have some pumping systems which your mass eccentricity is there, stiffness eccentricity is there, all this need to be really looked at. But if in just in the common term, the ground floor is essentially definitely is there, but is required to be placed at the upper stories also. In addition to that, if it is a 3 to 6 story structure, not necessary that the BRBs need to be placed all the floors. So it's a high energy capacity, or it has a higher potential. Only few floors use of the BRB will be adequate to take care of the energy demand. Other floors, the simple brace can work. Those brace can remain elastic also, not an issue.
So we can take two more questions. One is there a potential for use of BRB in offshore structures? That's one of the questions which is asked. That's asked by TN Shirish. Would you like to answer?
Yes. So in offshore structures, yes, it can be easily used. The only probably like the durability is one of the point needs to be taken care of. And so the material which we have been talking about, that is Fe based super elastic material, it has a better durability rather than only using the steel actually. So yeah, both can be used, but if it's need to be used for a more longer duration, I think some treatment needs to be done for the steel to prevent the corrosion, or it can be Fe based SMA plates. They are easily available in India right now.
Professor Tandon is asking a question that what parts can be reused after the earthquake?
Sorry, which what?
Mr. Mahesh Tandon is asking what parts can be reused after the earthquake?
Parts of the structure?
I'm just reading it out. So I guess he may be talking about the BRP. I don't know if Professor Tandon wants to elaborate.
Yeah,
Maybe
please.
he can ask us. Okay, one question I had is okay. Let me just first. There's one Mr. Sanjoy Chowdhury who's asking: is it a first kind of system. Can you please explain the innovation compared to existing tapping systems?
Yes. So in the self-centering system, yes, the material we are using, that is the something is novel. The second one, the buckling innovated shear panels. You need the casings, and those casings should actually relatively move. The upper part will move, relative to the other part. So the fabrication and the concept is completely new. The BRB as such, like till now, what people are using is a tube with some concrete and putting the steel plate as the core. But here, the way the casings have been developed, and to make that casing lightweight, we did some optimization. So that is the novelty in the BRB and the devices.
Great. Is there any other question? I'll ask one last question. If everybody is done. Okay. So my question is, Professor Sahoo, that going forward, what do you see as a potential use of these systems? Would it be more as retrofitting methodology, or would you also see in the future a case to be made for, greenfield projects? And I'm just thinking that, especially, I would assume that it could have a lot of potential for industrial projects also, steel buildings also, which right now I think, that sometimes these issues are being neglected, and the kind of calculations being done may not be very rigorous. So what is your view? Is it going to be just for retrofitting, or is it also for new design?
So it's essentially for both. I said that, but I believe that the new constructions or greenfield projects are more easier than the retrofitting projects. That's the way I see, because you have all sorts of flexibility to reorient your systems, redefine your systems. But in the retrofitting structures, when it is in use, and then based on our society, I'm looking at Indian context, it's not a very organized one, right? Like you have a structure, and then after 2 years, there are some extension all around actually. So there is a mass increase, there is a stiffness change. So yes, of course, so all these devices are effective in the new construction as well as the retrofitting construction. Uh, you know, but I think the retrofitting projects are essentially challenging. Like just looking at the structure, the way we have been doing sometimes, like FRP or strengthening, we have to go beyond that actually, and it needs proper planning. I think it needs more technical competence than the new structures actually, because changing any configuration during the planning stage is more easier than having a structure already built, used, and being modified.
Thanks so much. I think this was the last question we took, and now I'm going to hand over to our administrator, Sanjeev Kumar, for a vote of thanks. Sanjeev, we can't hear you. I think Sanjeev is having some uh, issues in connecting his audio. And I think Sanjeev has very succinctly put in the slide which says thank you. So, Sanjeev, if I may just do the honors on your behalf, I think we've had a very, very interesting session. We had Professor Jain first, kind of explaining the need for us engineers to stop just being technologists or technicians and raise the bar and also look at things more holistically. And for that, we must willy-nilly need to understand the entire gamut. We need to understand humanities. We need to understand economics. We need to ask the right questions, the why, the what, the how much, and not just how to do it, right? So I think that was a very important point which was made. And I think Professor Sahoo, I think very ably has demonstrated to us why he has got the SS Bhatnagar Award. I think it was, and look, I'm not at all being patronizing, but, Professor Sahoo, for all of us who've seen you as a student, I mean, I was coming to IIT Kanpur campus in 2001, 2002, and now to see where you are, it gives us so much pleasure. It gives us so much joy. And, for us, it's also about seeing that we passed on the baton to people who are far more capable than we are. And I think that's just amazing, the joy which we are getting. And we wish you all the best. And we hope that you achieve even greater heights. And you will also lead a whole team and the structural engineering community to likewise, go where you have been. Thank you so much. Really
Thank you.
appreciate and
Thank you.
and thanks to all of you. I know this was a Saturday evening, and and yet all of you have stayed and listened. But it was a very interesting lecture, and we will be putting it up on the SEFI website. So I think there were some questions they wanted to ask about a slide of yours. They wanted you to repeat it, and I've just responded that they can look at your program. And I'm sure if anybody has any questions they want to ask Dr. Sahoo, we will if you can just post it on SEFI, we will pass it on to him. Yeah, with
Sure.
this, I would like to thank everybody, and we can call this very interesting session to a close. Thank you very much. Bye.
Thank you.